Welcome to my YouTube channel. Today we will talk quickly about composition of functions, and then we will use that to define or to introduce the chain rule that will allow us to take derivatives of composite functions. We'll do a few examples and we'll finish with that. So let's get to it. So the first thing we're going to do is we're going to consider the domain of the function g. Let's call it just d of g, domain of g, let's call it. And let's pick an x, some number in there. And we're going to apply the function g to it. Of course, that is defined because we chose rather the x in that domain. So what we get as a result is g of x. That's what we normally would call it. Now, if g of x happens to be in the domain of the function f, then I can plug that number that I obtain from calculating g of x into, beautiful circle there, into g, and I get f of g of x. Now, there is a function that takes us directly from this x here to this number here, f of g of x, and we call that function the composite function. And we write it as f circle g, which would be the function g followed by f. That's another way of reading it. You read from right to left because the first function you'd be applying is the function g. So with that in place, then we can think about how can we take the derivative of such function. And the answer is by using the chain rule. So when you have the derivative of the function f circle g, is going to be f prime evaluated at g times g prime of x. The way I like reading this is saying the derivative of the outside, which is the function f, evaluated at the inside, which is going to be the function g, times the derivative of the inside, which is g prime. Just a quick example to see how it works. So we have h of x, and that's going to be, say, 3x plus 2 to the power of 4, for example, just to give an example. And we want to write this as a composition. And why would that be a composition of functions? Well, because this looks like it's a power of 4 here, but I have now a polynomial instead of just x in there. Polynomial degree 1, but nonetheless polynomial. So what we can do is identify what the outside function will be. The outside function will be that x to the 4th. We're just grabbing a variable, which is x in this case, and raising it to the power of 4. So that gives us our function. And just for the sake of illustrating better what's happening, let's put a 5 in here. Then the function would be 5x to the 4th. So what I'm saying is whatever I do to this x is going to go in this parentheses. Now, what is that parentheses? Well, that's going to be your inside function, which is going to be 3x plus 2. So you can check that this is going to be actually f evaluated at g of x, or if you want to write it in terms of composition, f circle g of x. So now our derivative, or just h prime if you prefer, would simply be taking the derivative of f, let's compute that here, which is going to be 20 x cubed, that is just power rule, grabbing 4 times 5 and then subtracting 1 from 4, and then g prime is just going to be 3. So now plugging everything into place. F prime, let's write out everything that it would be. F prime evaluated at g of x times g prime evaluated at x. Now f prime at g of x is going to be 20 times whatever I plug in terms of g cubed. So what is going to be g? Okay, sorry about that scroll. So g would go here, and g is simply this function that I here, so that I have there. So just the inside function that we originally had gets to be copied in place. So basically, I treat that at the moment as if it's just 5x to the 4th and copy that 3x plus 2. Now, the difference comes from whenever I have whatever I have after, which I think about it as, well, I didn't have just x here, I had 3x plus 2, so I need to pay a price for using the rule for it, and I think about it as a tax, and that tax happens to be g prime. In this case, it would be times 3, which is g prime. So putting it together, we get 60 3x plus 2 cubed, and that would be our answer. So now we're going to start with a few examples. So we're going to do the review on chain rule. So we're going to start with this problem, typical problem of chain rule, where you have a power of 5 here. So at this point, foiling this out would be already too much. So we're going to do that. We're going to compute this derivative by using chain rule. So the outside function would be, unfortunately this doesn't work with a highlighter, but the outside function would be this here, power to the 5th. So the function that we would have outside would be x to the 5th. Now the function that would go inside, or the one we're going to be taking or putting inside of f, will, or g rather, will be h, which would be just 2x to the 4th minus 2x squared. So then we remember we need to take the derivatives. So in this case, I do power rule, so I drop the 5, subtract 1 from the exponent, and I get that derivative. Now for this derivative, I just compute the derivative of each term using power rule, so drop the 4, multiply times 2 is going to be 8. X to the 4 minus 1 is going to be 3. And then I'm going to have minus 2 times 2, 4. X to the 2 minus 1, 1. So I get that. So now the derivative, we're going to use all this. Remember the derivative, we're going to have the derivative of the outside evaluated rather at the inside. And that, by the way, is a very common mistake, just writing the derivative of the function and then multiplying times the derivative of the function itself, a function the inside. So when we plug this in, g prime would be 5, but instead of x, I have to leave h of x there to the power of 4 times h prime, which is going to be 8x cubed minus 4x. And what do I put in this parenthesis? I put h, so the inside function. I don't put the derivative of the function, but the inside function only. Of course, if I had given myself more room, would have been great. All right, so here we can factor and simplify, but we're just not going to do that because we're focusing on the procedure itself. Now, what are common mistakes that you guys, or that I've been seeing on the worksheets? So the first one would be taking the derivative of g. So you get 5 to the power of 4, but instead of plugging h of x, what I've been seeing is that people are plugging in h prime. So you're plugging in the derivative here and then leaving it at that. So that, instead of being what we have here as the chain rule, what that would be g prime evaluated at h prime. That is not right. So that's one common mistake that you want to avoid. Another common mistake that I've been seeing is, for example, taking the derivative of g, so writing 5x to the 4th, and then instead of evaluating that 5x to the 4th at h, just multiplying that h out. And then, of course, the h prime comes around, which would be 8x cubed minus 4x. What would this be? This would be g prime evaluated at x, and then times h of x times h prime of x. These two are not the same as what we have here. So this is another typical mistake. So what you want to do is, again, let's repeat it. You take your derivative of the g prime, so 5x to the fourth, but now you, instead of plugging x, you're going to leave that room to plug the inside of the function again. So 2x to the fourth minus 2x squared. This time you see I learned, I left myself enough room, times h prime, which is going to be 8x cubed minus 4x. And that gives us right there the derivative. So for this problem, one alternative that people did was basically doing a chain rule here. Sorry, quotient rule rather. So take the derivative here, and then you would take the derivative of the top, so 0 times the bottom, so root fourth of 2x to the fourth minus 5x squared, then minus, that's going to be 0, that term, and then you're going to have minus the derivative of the bottom minus 5x squared times the top, times 1. All over the bottom squared, so this would be now the square root of, because it would be to the fourth, or fourth root squared would be just the square root. And while this is all true, I would completely discourage you from doing it this way, because it's way too difficult. Instead, you can write this as 2x to the fourth minus 5x squared to the power of negative 1/4. And now you can apply chain rule to this expression, which is a lot easier than what we had down there. So so please be mindful of that. That would make your life a lot easier if you avoid that mistake. Or it's not really a mistake, it's just you're complicating things more than you need to. So first thing, if you can algebraically simplify the expression in some sort of way, do that. And in this particular case, we can do it. Another typical case when this is done is when you have things of the form 1 over x, I don't know, to the 9th, whatever. And people usually do quotient rule for this because, after all, it's a quotient, but it would be a lot easier if you write this as x to the negative 9th. That would make your life easier. Then you take the derivative just using power rule instead of doing a quotient rule. So always try to simplify things in order to use less differentiation techniques rather than more. So in this case, the simplification would be just writing this as a negative 1/4, and then your derivative follows from just doing a chain rule where the outside function would be your, let's call it g of x again, x to the negative 1/4, and your derivative there would be negative 1/4, so you drop that, times x to the negative 1/4 minus 1, so negative 5/4. So that would be your derivative, and then over the outside, and then the inside would be this right here, which we're going to call h, and that would be 2x to the fourth minus 5x squared, where our derivative now is just using the power rule. So 4 times 2, 8, x to the 4 minus 1, 3, minus 2 times 5, 10, x to the 2 minus 1, 1. So leave it like that. And so we put it together. Let's remember what the derivative would be. The derivative would be the derivative of the outside. I guess I keep doing that. Evaluated at the inside. And then times derivative of the inside. So putting this together in this case, I think we can fit it here, would be negative 1/4. And then the space for the function that we're going to write to the power of negative 5/4. So in here, we have two options, h or h prime. Remember, it's going to be h. So typical mistake is plugging h prime, as I told you before. So plug in just h times h prime. And of course, this can be simplified again, factoring x squared from this one, factoring x from this one, multiplying everything. We're going to leave it at that. I think this one is good enough. So for this one, well, I forgot I copied the answer from the practice problem list, so there it is. And we even have the simplified version here, so you know it's good. So this is another one of those where you have a number in the numerator and a function in the denominator, so you can just write this as the function to the negative one, and that may help you solve it easier. So let's do that. So in this case, it would be x to the fifth minus x cubed, and the function to the negative 1 becomes negative 2/3. The exponent on that one would be negative 2/3. So that gives us a function that we can work with. So now this time I'm gonna just go ahead and, because we already did quite a few, I'm just gonna mention what we're gonna do. So we're gonna drop the negative 2/3, and we're going to put the parentheses for the function, and we're going to now raise it to the power of negative 2/3 minus 1, so negative 5/3. And then we copy the inside function. So this is the most common mistake that people forget what goes in here and put different things. Is the same function you had here, you put that same function here. So this is the same as this. And now you multiply times the derivative of that function, the inside. So 5x to the fourth by using power rule here, dropping the 5, subtracting 1 from the exponent, minus drop the 3, subtract 1 from the exponent, 3 minus 1, 2, and you get your derivative right there. So that one, now that we didn't separate and write out all the functions because we are getting used to it, is probably a lot easier.